Hi, everybody. Thank you for coming. I know it's the end of the day. I appreciate all of you being here to see my talk, Insights into Customer Behavior from Clickstream Data. My name is RJ Noling, and I'm a software engineer at Red Hat. I'm on the data science team in emerging technologies. We evaluate solutions in the open source big data space, ensure those solutions work with Red Hat products for Red Hat customers, and promote data science internally at Red Hat through consulting efforts. I'm also a member of the Apache Big Top PMC. Today I want to talk to you about Clickstream Data. Red Hat has collected page view data across its online properties for the last few years. This has led to a data set with 61 million page views by 125,000 customers across 500,000 pages. Of those 500,000 pages, 125,000 are knowledge base articles. This data set has numerous potential applications within Red Hat. We could build customer profiles to aid our sales teams. We could build a recommendation system for our knowledge base. We can improve customer portal search to ensure that customers are getting the most relevant results. And we could guide selection of new knowledge base topics to help our content writers out. But today, I actually want to talk to you about combining that Clickstream data with topic modeling of our knowledge base articles to look at what topics customers are interested in. This talk will have three parts. The first part, I'll be talking about our pipeline for topic modeling of our knowledge base articles. In the second part, I'll talk about the pipeline for analyzing the Clickstream data and projecting it onto the topics. In the last part of the presentation, I'll go over some of the lessons learned along the way that you might find helpful as well. So let's get started. Red Hat stores all of its knowledge base articles as markdown documents, following a particular structure. So in order to do topic modeling, the first thing we need to do is actually strip the markdown formatting and punctuation, like so. The second step is to identify words that have multiple forms, such as singular versus plural, or a conjugation of verbs, and map them all to a single form. A common approach for doing this is to use a stemming algorithm that reduces each word to its root stem. Unfortunately, we found that this didn't work very well for our technical vocabulary. For example, NFS, for network file system, was assumed to be plural and reduced to NF. Instead, I looked at most frequently occurring words and built up a manual list of words that to be replaced and what they should be replaced with. So for example, types, packages, contains, following. These are replaced with type, package, contain, follow. The next step are to remove words that add no semantic meaning. These are often called stop words. What, are, the, of, in, articles, things like that. Once again, I built up a manual list and filtered these words out of the documents. This leaves us with the words we actually use for the topic modeling, those with a semantic meaning. So the next step is to convert this list of words for each document into word count vectors. So for example, the word kernel appears 5 times in this document. Red occurs 4 times. Hat occurs 4 times. I found that 75% of the words in our vocabulary across all the documents appear in fewer than 5 documents total. So I filtered all of these out, significantly reducing our computational requirements and memory usage. With what was left, we modeled each document using a sparse vector, where the index corresponded to a word in our vocabulary across all of the documents, and the element corresponded with the number of times each word appeared. I transformed these vectors using an inverse document frequency and then normalized them. At this point, I clustered all of the documents. The black points represent the cluster centers, and the cyan points represent the documents. I assumed that each cluster had one topic and identified the words associated with those topics by identifying which words were enriched. I did this by subtracting the average of the normalized word count vectors outside of each cluster from the average of the normalized word count vectors inside each cluster, giving each word an enrichment score between 1 and -1. 1 indicating that a word only appears within that cluster, and -1 indicating the word only appears outside of the cluster. I then sorted the words by their enrichment values and took the top 10 words above a specific threshold. giving me topics like so. Here I have 4 topics, 3 of which correspond to our products. The first topic, OpenShift Gear Cartridge Online Node Broker. OpenShift is Red Hat's platform as a service product, available in an on-premise form called OpenShift Dedicated and a hosted form called OpenShift Online. So you can see the topic is capturing OpenShift and online. Gear corresponds to a running application, and a cartridge is a way of providing common services such as MySQL or the JBoss web server to running applications. So this topic captures a number of those concepts quite well. Our second topic, VM for virtual machine, RED for Red Hat Enterprise Virtualization, virtualization disk. This captures our Rev product pretty well. Gluster FS. Gluster is one of 2 distributed file systems that Red Hat sells as part of its Red Hat Storage suite of products. Here we see storage and RHS corresponding to Red Hat Storage. Volume and Brick correspond to how Gluster organizes and exports storage to the clients. Glusterd, Node, Client, Mount, Geo. Geo for geo-replicated. Our fourth topic doesn't correspond to a product, it corresponds to hardware support. So RHEL for Red Hat Enterprise Linux, support, driver, HP, hardware, version, firmware, card, Intel. This corresponds to documents like, how do I install the the drivers for my NVIDIA graphics card? All of these topics have certain desirable properties. They're interpretable, they're composable. So for example, we could have a customer who's running OpenShift on top of Red Hat Enterprise Virtualization, and they're distinct. I was interested in how many articles are written for each topic. So I took the top enriched word for each topic and produced a word cloud where the sizes of the words indicate how many relative number of articles. We see that JBoss, Rev, RHEL, and Satellite, 4 of our products are among those topics with the most words, or most articles. We also see other topics such as network, log, memory, and device have a number of articles written, which makes sense. Customers are interested in formatting a file system on top of a device, or configuring a network, since we sell operating systems and platforms, or accessing log data, or issues with the kernel. Next, I'd like to talk about the pipeline we actually use for processing the Clickstream data and projecting it onto the topics. Every day's activities are stored as a single gzipped tab-separated value file. These files need to be extracted and parsed so that we can then process them in Spark. We then clean and filter the records. So we remove records with bad data, fill in missing values, and then clean the URLs, removing prefixes such as HTTP and HTTPS, and suffixes such as the session ID that would impair our ability to aggregate. We also filter the URLs, keeping only those URLs corresponding to our knowledge base articles. At this point, we join the data with our account data and perform an aggregation so that we get triplets of the account, the URL, and the number of times that URL was viewed by that account. From our previous work, we know which documents or pages correspond to which topics. So we use that to project our page views onto the topics and perform one more aggregation, giving us triplets of the customer, the topic, and the number of times the topic was viewed. We then cluster the customers by the topic views, giving us customer profiles. In analyzing these profiles, I've noticed a number of trends. The first is that there are a number of topics which are dominant topics. These topics are highly enriched within a single cluster, far more enriched than any of the other topics appearing in that cluster. Example are JBoss, Red Hat Enterprise Virtualization, and Gluster. But it's not just products. Hardware support, booting into rescue mode, so apparently a number of users mess up Grub or something like that, and packages. How do I add a repository? How do I find a package? How do I install a package? Some of our topics are supporting topics. They tend not to be as highly enriched within a single cluster and appear in combination with multiple topics across clusters. Example, logging, LDAP, which is the directory service, Samba for Windows file sharing, questions about high resource usage, questions about formatting a file system, setting up the logical volume manager or block devices, and questions around configuring networks or diagnosing network issues. Some products tend to appear in combination. For example, JBoss and Red Hat Enterprise Virtualization. So some of these customers might be developing enterprise applications with JBoss and then deploying them to a cluster that's managed by Red Hat Enterprise Virtualization. Some of the products only appear by themselves, though. They may appear with supporting topics, but not other products. Examples are OpenShift and Gluster. These are newer products. They may not have as many articles written about them, so they may not be appearing as highly in the results. And they may not be as many customers using them, particularly in combination with other products. These represent cross-sell opportunities for our sales teams. We may be able to say, okay, you're running JBoss on Rev, maybe it would be easier to deploy using OpenShift, and maybe you want to use Gluster for storage. Here, I look at the enrichment of the topics relative to the number of articles. What I mean is I would expect the number of articles to be proportional to the number of times a topic is viewed. In fact, I found that certain topics tend to be viewed much more frequently than the number of articles they have suggest. For example, VM for virtual machine, Tomcat, which is the JBoss web server, volume corresponding to file systems and devices, and fencing. Fencing, of course, has to do with when we set up a high availability cluster and one of the nodes misbehaves, that node is automatically disconnected from the cluster in a process called fencing. Some of our least viewed topics, even though there are a large number of articles about them, are about the Apache web server HTTPD and the FTP server VSFTPD. Linux rose to prominence as a platform for running web services, LAMP, Linux, Apache, MySQL, PHP. But as Red Hat has grown, our customer base has diversified, and a number of additional use cases have popped up. As such, a number of these articles have been written about the Apache web server and the FTP web server quite a while ago, and are viewed less frequently now than they were originally. Along the way of doing this work, I learned a few lessons. One is that, as I mentioned, the page view data itself is stored as gzip files. And these need to be read sequentially, so our performance comes from reading multiple files in parallel. These files are tab separated with no quoting. That means all new line characters and all tabs need to be escaped. Unfortunately, our records also contain improperly escaped tabs and new lines, as well as extraneous unmatched quote marks. The Spark CSV package depends on Spark's text file reader, which isn't aware of escaping. When it sees a new line, it assumes that's the end of one record and the beginning of the next. The Spark CSV library also uses the Apache Common, the Spark CSV library also uses the Apache Common CSV library to parse the records once they're read in. It's it's not a very flexible parser, and so if you tell it that the records don't contain new line, or don't contain quote marks, but it comes across a quote mark, it throws an exception. It's not the most flexible of parsers. So we wrote a custom Hadoop input format, something that's aware of the escaping and can handle records with escaped new line characters. We handle some of the other details, such as the extraneous quote marks in our later cleaning phases. The custom Hadoop input format is also able to handle the improperly escaped tabs and new lines and replace them with the properly escaped versions. The second lesson is verify everything. What works in general may not work for you. I mentioned some of the issues we ran into with the stemming algorithms, a common approach in natural language processing. I also discussed the fact that blindly filtering out the most frequent words would have removed words that are relevant to our topics, such as Linux or kernel. I found tutorials that actually suggested removing the words that occur in more than 95% of documents. So be careful of doing that. I also mentioned using k-means to cluster the documents. If you look at most tutorials on topic modeling, they discuss latent dirichlet allocation, or LDA. Remember that our requirements for the topics were that they were composable, distinct, and easily interpretable. When we use LDA, we actually found that it produced topics that weren't composable, weren't very distinct, and weren't easily interpreted. For example, one of the topics from LDA had the words OpenShift, CloudForms, and satellite. My interpretation of this is this refers to customers who are provisioning their physical machines using Red Hat Satellite, installing OpenShift on top of it, and managing their clusters with ManageIQ. But this represents a very specific set of customers. It's not composable with other topics. We found that k-means worked better than LDA in our case. In terms of k-means itself, I suggest using multiple runs and more iterations than the default parameters suggest. This significantly reduced the error in our clustering and gave us consistent results across runs. Also, watch out for memory leaks. In Spark 1.4 and earlier, the k-means implementation cached a number of RDDs, but never unpersisted them when it was done. When I was doing a sweep over the parameter for the number of clusters, I ran out of memory. Newer versions of Spark, such as Spark 1.5, 1.6, incorporate patches that actually unpersist all of these cached RDDs. I actually submitted a patch to build on top of this work to unpersist the broadcasted variables, in particular the cluster centers as well. Why? Because we're working with sparse vectors, but the k-means implementation uses dense vectors for the cluster centers. We have a high degree of sparsity in our data set, and so the materialization of the dense vectors for a large number of cluster centers quickly ate up memory. So that by persisting those broadcasted variables after every iteration of the k-means algorithm, we improve memory usage. Along the way, we also found that the component of our pipeline for processing the Clickstream data that handled the extraction and parsing of the tab-separated value files was responsible for a significant portion of computational effort and memory usage. We found that actually separating that component out from the rest of the pipeline and writing the results out to the Parquet file format significantly improved memory usage in the rest of the pipeline, since Parquet enables you to read only the data you need, and Spark data frames are optimized to only read optimized to read only the data you need using Parquet's capabilities. Prior, when we tried to do it as a single pipeline, we actually would run out of memory issues. It would be much slower because Spark would start running out of memory and start doing garbage collection to evict things from the cache. So by doing it this way, we significantly improved our performance. At the beginning of the talk, I mentioned several potential applications: building customer profiles to aid our sales teams, building a recommendation system for our knowledge base, improving customer portal search, and guiding selection of new knowledge base topics to help our content writers. I'm currently working with the techniques I developed through this project to aid in these efforts and working with internal groups to promote this at Red Hat. This sort of work is valuable and pays back in multiple fold. I'll be uploading a copy of my slides to my blog. Check it out. I occasionally have blog posts about projects like this at Red Hat and what we're doing. Thank you for your time today, and if there are any questions, I'd be happy to take them.
Excellent presentation. Any questions? Please raise your hand and I'll come over with the mic.
I think she is a...
How do you spread up the data into different machines?
What do you mean? Well, so each day is one single gzip file, right? So we have several years worth of data. So we have 1,000 files, 1,200 files, something like that. So then it's still parallelized. It's just normally the Hadoop file reader chunks up a single file. In this case, we're not chunking up the files. We're just reading X number of them in parallel. Does that make any sense? I mean, Spark does the distributed computation for us.
Right, but when you do k-means clustering, you do in the same machine, right? How do you spread up for different machines?
Well, we have a cluster of like 10 nodes, and we just do all the processing on that. Each node has 400 gigs of memory and 20 cores. So I'm sorry, I'm not really answering your question well, I guess.
I think the question was basically considering how is the distribution of Spark k-means itself. So the underlying k-means code actually handles the distribution itself.
Yeah.
That's the question. So,
Are there any other questions?
any other questions, guys? Yeah, sure, go for it. Sorry.
That was a good talk, thank you.
Thanks.
So being at Red Hat, I assume you're pretty good with sysadmin and tuning Spark. Any advice for how to tune the JVM to kind of have good results?
Okay, so actually I am the system administrator for our small cluster, but I'm not an expert in everything. I would actually, my colleague Will Benton has written his blog about this as well. But one thing is, think about your memory usage. In particular, you can specify the amount of memory per executor in the driver, right? So that's one thing. The second thing is you can control, there's a parameter for controlling how much memory is dedicated to cached data versus what's being used. Do that. Big one is control the number, be aware of the number of partitions. So for particularly in k-means, one of the problems we ran into is we only had 2 or 3 partitions at one point. So the way Spark works, it only uses 1 thread per partition. So the more partitions you have, the better able it is to parallelize your processing. The Parquet format, once again, another great thing because it allows you to only read in the data you need for the computation, and Spark's data frames are pretty good at optimizing that. The YourKit profiler is fantastic for looking at your code and realizing where it's spending time. Yeah, those are some of the key things. Do you have any other sort of performance questions in particular?
I'll catch you offline.
All right, sounds great.
Cool. Any other questions? All right, well then, thank you very much, everybody.